Imagine the world without metal, no phones, no cars, no skyscrapers. What would you do? Today we pull back the curtain on the amazing journey from rock to the metal in your hand. Look around you right now. Your phone, your chair, the car outside. Everything relies on something we take for granted, metal. What if all the metal in the world vanished overnight? Poof. Houses crumble, the power grid fails, transportation grinds to a halt. Metal is the silent backbone of civilization. Strength, conductivity, malleability, durability. From the tiniest screw to the beams that scrape the sky. But how does dull rock become gleaming metal? It starts deep beneath our feet. Ready to get your hands dirty and dive in? Let's pull back the curtain. Chapter 1. From Earth to Ore. Geologists use satellite imagery, seismic sensors, and mapping to hunt for ore. Sometimes we carve giant terraced bowls, open-pit mining, with machines bigger than houses. Other times, miners tunnel deep, drilling and blasting to follow ore veins. Then the ore is hauled to the surface and trucked to plants. But it still looks like rock. Next, the fire that frees the metal. Ores are rocks rich in metal, but the metal is chemically bonded to other elements. Often it's bound to oxygen, sulfur, think iron oxide, rust. Finding and extracting ore is a massive engineering challenge. Pits miles wide, shafts that go deep. Haul trucks, excavators, and dozers move mountains of earth. Two main methods: open pit for near-surface deposits, underground for deep veins. Underground miners drill, blast, and use skips to bring ore up. Ore gets crushed, sorted, and transported to processing plants. Crushing increases surface area so chemistry can be applied efficiently. Plants use flotation, magnetic separation, and other methods to concentrate the metal-bearing material. The result? A concentrated ore ready for smelting. From here, the journey heads to the furnace, where fire and chemistry separate metal from rock. Next, smelting, industrial alchemy. It's dramatic, molten rivers of metal. You'll see how we use heat, flux, and chemistry. What metal surprised you most? Drop a quick thought below. We'll answer in the end. Now, the fire. Chapter 2. The magic of smelting. Where we use heat to free the metal from rock. It's gritty and heavy but full of metal hidden inside. A blast furnace is a towering silo lined with fire brick. Ore, coke, and limestone are loaded from the top. Powerful jets blast superheated air. Temperatures climb to roughly 1,650 degrees Celsius. Carbon from coke bonds with oxygen in the ore, producing carbon monoxide and freeing metal atoms. Freed metal melts and sinks. Molten impurities float as slag. Coke provides heat and carbon. Limestone acts as flux to collect impurities. Molten slag is tapped off, waste that's separated from the metal. Then the furnace is tapped, and a glowing river of metal pours out. One of industry's most spectacular sights. The molten prize is moved by cranes to finishing lines. Refining occurs in vessels like the basic oxygen furnace, where oxygen burns impurities. Or electric arc furnaces recycle scrap with blazing arcs of electricity. A heavy, purer metal layer sits underneath a floating slag layer, two liquids, different densities. Technicians sample and adjust chemistry constantly to hit target grades. Once refined, the liquid metal is formed. Continuous casting turns liquid into slabs, billets, and beams. Next, turning molten soup into solid steel. Chapter 3. From molten soup to solid steel. The refining and shaping stage. Metallurgists tweak the recipe. Tiny additions make huge differences. Add chromium for corrosion resistance, nickel for toughness, manganese for ductility, vanadium for strength. A little carbon turns iron into steel, much stronger and more useful. Basic oxygen furnaces burn impurities. Electric arc furnaces recycle scrap. Operators monitor chemistry constantly, precision at enormous scale. The molten stream enters a water-cooled mold and begins to solidify. It becomes slabs, billets, or beams, still red-hot and workable. Cranes move cast shapes to rolling mills where pressure refines structure. Rollers squeeze and stretch, thin sheets for cars, rails for trains, beams for buildings. Rolling changes internal grain structure. This is what gives steel its strength. Non-destructive testing and lab checks ensure specs are met. From ore to engineered materials, the metal is ready to build skyscrapers, cars, and railways. It's an epic transformation, rock to structure. Next, how this metal ends up in the tools, gadgets, and structures you use every day. Chapter 4. Metal is everywhere. Chapter 4. Metal is everywhere. In your fork, your car, your phone. Tiny traces of copper, gold, indium, and tin make your devices sing. Take a fork. Chromium and nickel and stainless steel prevent rust in your dishwasher. Aluminum cans are thin, light, and strong, engineered from rolled sheet. Cars use aluminum for body panels and hardened steel for chassis and safety. Airplanes use advanced aluminum and titanium alloys for strength-to-weight performance. Electronics depend on tiny amounts of precious metals, gold for corrosion-free contacts. Even undersea fiber is protected by steel sheathing. Metal underpins global networks. Open a door, turn on a tap, ride your bike. Metal is working quietly in all of them. Keys, coins, clips. Imagine counting all the metals you touch today. In medicine, titanium implants save and restore lives. In space, superalloys and lightweight foams push exploration forward. Researchers create memory metals, metal foams, and superalloys with incredible properties. The future of engineering and medicine is built on new metal science. Next time you touch metal, remember the journey, from deep earth to your hand. One more chapter, how metal gets a second life. Chapter 5. Metal's story doesn't end. It's one of the most recyclable materials on Earth. Aluminum can be back on the shelf in as little as 60 days, and recycling uses far less energy. Giant magnets pull iron and steel. Other metals are separated, shredded, and melted. Shredded metal goes back into furnaces and out as new ingots. Making metal from scrap uses dramatically less energy than from raw ore, especially for aluminum, 95% less. It's better for the planet and good for business. Closed-loop manufacturing. Scientists keep inventing superalloys, metal foams, shape memory metals, and more. These advances power jet engines, implants, and spacecraft. From mountain to molten metal to engineered products, rock transformed by fire and force. I hope this peek behind the curtain gave you a new appreciation. Tell me, what surprised you? The mines, the heat, or the precision of alloys? What everyday item should we take apart next? Suggest it below. If you enjoyed this deep dive, like, subscribe, share, and comment. Your support helps us make more explainers. Hit the bell and tell us what to explore next. Metallurgy, recycling, or aerospace alloys? Metal, ancient, futuristic, and always at the heart of our world. See you in the next video.